Today under statistical thermodynamics, we will be looking at the partition function in terms of thermodynamic functions, and today we will be looking at two of the thermodynamic functions. One is internal energy and another is heat capacity. So internal energy E of the system, it is given as N0 E0 plus N1 E1 and so on. So this is when we are distributing total n number of particles between EI amount of energy states, then this is the distribution and the total energy is written as E, and hence we could write E is equal to summation EI Ni Maxwell-Boltzmann distribution law, that is Ni upon N is equal to Gi e raised to minus beta Ei upon summation Gi e raised to minus beta Ei, and this lower term is the partition function. Also beta, we know it is equal to 1 upon kt. So we will be substituting this, that is this n will go over here, and all ni we will be substituting the value of ni, that is n upon q, that is the whole denominator I have written it equal to q. We have gi e raised to minus ei upon kt. Further n and q are constant, so it will come out of the summation. So n by q is equal to summation ei e raised to minus ei upon kt into gi, and we know this is the partition function. So q is equal to summation gi e raised to minus ei by kt. Now we will differentiate this with respect to the temperature, and when we differentiate it, the differentiation dq by dt we will get is 1 upon kt square summation ei gi e raised to minus ei by kt. Differentiation of e raised to minus ei by kt will be minus ei, and again minus ei by k, and 1 upon t will be differentiated, and 1 upon t will be again minus 1 upon t square. So this minus and this minus will become plus, and hence we will have 1 upon kt square summation ei gi e raised to minus ei by minus ei upon kt. Now we will rearrange this in the form of summation ei gi e raised to minus e. That means kt square will go on right hand side, and hence we will have this term. Now this already we have over here, that is this particular term. So this we will be substituting it over here, and hence we will have n by q into kt square dq by dt, and we all know that dq by q, it could be written as dln of q. So dq by q is written as dln of q by t and nkt. Now where suppose n are 1 mole, if we are taking n is 1 mole, then 1 mole is equal to Avogadro's number, that is it could be written as n. So for n I am substituting capital N, which represents the Avogadro's number, k is Boltzmann constant, and T is the temperature. Also we know that Boltzmann constant k is equal to R by n, or we could write R is equal to k into n. So this n into k, it will be substituted as R, where R is the real gas constant, RT square dln q by dt at constant volume, and this is the final expression for our internal energy in terms of partition function q. Now in few books it is written as small q, in few books it is written as capital Q, and so on. Next is the heat capacity in terms of partition function, and heat capacity we will be looking at heat capacity at constant volume, that is Cv. So we know that Cv, heat capacity at constant volume, is dE by dt at constant volume, and if we want heat capacity at constant pressure, then it is dH by dt at constant pressure. So we'll be looking only at heat capacity at constant volume. So we have the value of internal energy, and that is nkt square dln q by dt. So we'll be differentiating this. Now this could be written as R also. So the constant terms I am taking out, there is n and k are constant, so it is taken out. We could write R also. So for 1 mole of the system, we could write it as R also. So differentiation with respect to temperature into T square dln q by dt at constant volume. So this is the value of heat capacity at constant volume in terms of partition function. Thank you.